When the Nobel Prize in Physics is announced each year, the world holds its breath. It's a moment when science takes center stage, when the brightest minds are celebrated for uncovering truths about the universe. But what if one of those truths turned out to be wrong? What if a discovery so groundbreaking that it earned the highest honor in science was later proven false? This is not a hypothetical scenario. It happened, and it shook the scientific community to its core. This is the story of the 2011 Nobel Prize in story that began with awe-inspiring discoveries about the expansion of our universe and ended with a growing debate over whether we truly understand the cosmos at all. In 2011, the Nobel Committee awarded the prize to 3 astrophysicists: Saul Perlmutter, Brian Schmidt, and Adam Rees. Their work changed everything we thought we knew about the universe's fate. They were celebrated for discovering that the expansion of the universe wasn't slowing down, as once believed, but was actually accelerating. And that acceleration, they said, was being driven by something mysterious called dark energy. The concept of dark energy wasn't entirely new, but before 2011, it was mostly theoretical. These scientists, using distant supernova as cosmic markers, provided what seemed like concrete evidence. By measuring the brightness and redshift of Type Ia supernova stellar explosions that act like reliable cosmic mile markers, they noticed something astonishing. The supernova were dimmer than expected, suggesting they were farther away than they should be if the universe's expansion was constant or slowing down. This led to one breathtaking conclusion. The universe's expansion was speeding up, and whatever was causing that acceleration, this unknown, invisible force, was dubbed dark energy. It was an elegant solution, and it stunned the world. Their findings didn't just earn them Nobel medals, it reshaped cosmology. Dark energy was inserted into the standard model of cosmology, accounting for nearly 70% of everything in existence. But here's where the story takes a turn. Over a decade after that Nobel-winning discovery, cracks began to form. A growing number of physicists and astronomers began to ask hard questions. What if the data was being misinterpreted? What if our assumptions about Type Ia supernova weren't as reliable as we thought? What if dark energy wasn't real? At the heart of the problem was this: the universe's expansion isn't something we can watch in real time. It's something we infer through light that has traveled across billions of years. And interpreting that light depends on models. If the models are off, the conclusions might be two. One major challenge came from the so-called Hubble tension. 2 different methods of measuring the universe's expansion rate, one using the cosmic microwave background from the early universe, and another using supernova and local galaxies, were producing results that didn't agree. If dark energy was real and accelerating the universe, the 2 measurements should align, but they didn't. And the discrepancy kept growing. Some scientists began proposing alternative theories. One suggestion: maybe the universe's acceleration isn't due to a mysterious force, but 2 flaws in our interpretation of the data. Could it be that the supernova used in the Nobel research weren't as standard as believed? Perhaps their brightness varies more than previously assumed. Or maybe there are other factors like cosmic dust, galaxy. Another idea: maybe we relocated in a cosmic bubble, a rare region of lower density in the universe. If that were true, the light we see from distant galaxies might give the illusion of acceleration when, in reality, we're just seeing a local quirk in the cosmic landscape. More radical theories propose modifying the laws of gravity. If Einstein's general relativity isn't quite right on cosmological scales, maybe what we call dark energy is actually a consequence of that incomplete understanding. Some physicists are working on so-called modified gravity models that attempt to explain the acceleration without invoking dark energy at all. In 2023, a bombshell paper from researchers at the University of Copenhagen reignited the debate. After reanalyzing supernova data with newer models, they concluded there was no significant evidence for cosmic acceleration. That meant dark energy might not exist. The Nobel-winning conclusion could be wrong. The implications were staggering. If dark energy doesn't exist, our entire understanding of the cosmos has to be revised. Everything from the ultimate fate of the universe to our theories of spacetime and gravity would be in flux. It would be one of the greatest scientific reversals in modern history. And that raises a deeper, more uncomfortable question. What does it mean to win a Nobel Prize for something that might not be true? Science, unlike many human endeavors, doesn't claim it refines itself. But when the Nobel Prize, the gold standard of credibility, is awarded, the public takes that as proof of certainty. When that certainty unravels, trust is shaken. Some argue this is just how science works. The Nobel wasn't a mistake. They said was recognition of the best interpretation of evidence at the time. The discovery of cosmic acceleration was real, even if our understanding of its cause, dark energy, turns out to be flawed. Others say the system needs to slow down. Science thrives on skepticism, on replication, on time. In a world of rapidly rewarded breakthroughs, there's a danger in celebrating conclusions too soon. Even brilliant minds can misread the cosmos. But this story also reveals something beautiful about science. The fact that a Nobel Prize can be questioned doesn't diminish its value. It underscores science's strength. Unlike dogma, science invites correction. It allows the possibility of being wrong. That's what drives progress. And now, the cosmos has placed us at another crossroad. If dark energy is real, we must uncover its nature. What is this force that dominates the universe? It cannot be seen. Could it be linked to quantum fields? Could it reveal new dimensions or tie into string theory? Some researchers believe that solving the mystery of dark energy may lead to a theory of everything, a unification of gravity and quantum mechanics. If dark energy is not real, then the universe is whispering something even more profound, that our models are broken, that our assumptions are wrong, and that we may be on the verge of a scientific revolution. In either case, we're standing on the edge of a new understanding. Just as Einstein rewrote Newton and quantum mechanics rewrote classical physics, the next few decades may completely rewrite cosmology. The story of the accelerating universe isn't over. It's just beginning a new chapter. And you watching this, questioning with us, are part of that story. As space telescopes like the James Webb, Euclid, and the upcoming Nancy Grace Roman Observatory gather fresh data, we will move closer to the truth. Whether that truth confirms dark energy or dismantles it, the pursuit itself is what defines us as explorers. So the next time you hear the words Nobel Prize, remember, it's not the end of the journey. It's a milestone along a path that winds through mystery, wonder, and the great unknown. Because in science, even when we're wrong, we're still moving forward. And if you enjoyed this deep dive into the mysteries of our universe, make sure to like this video, subscribe to Beyond Stars, and hit the bell so you never miss a journey into the cosmos. Thanks for watching.